Hello ladies and gentlemen, this is Mr. Cunningham, and what we're going to be talking about today is the mole. So what you should have is a notes page that's labeled at the top Lesson 10.1, the mole and molar mass. So you can follow along on that notes page. That way you kind of have something to keep track of so you know kind of what's important for this lesson. So at the top of that page you'll see two sub-objectives. I'll be trying to do this a lot, is adding objectives, sub-objectives, and goals so that you guys know what you should get out of each video. So here are the sub-objectives. First of all, you should know the number of particles in a mole after you're done with this video. Sub-objective 2, you should be able to determine the molar mass of a substance. And then our goal is be able to determine the number of moles given the number of particles and vice versa. So basically I'm asking you to convert back and forth between moles and particles. So let's get started. So the first thing that we're going to talk about is something called Avogadro's number. So Avogadro's number is the number of atoms, like this is the actual definition of what Avogadro's number is the number of atoms in 12.01 grams of carbon. Now that number actually turns out to be 6.02 times 10 to the 23rd. Okay, so in other words, there are 6.02 times 10 to the 23rd atoms in 12.01 grams of carbon. Okay? So that means that there's a ton of particles. I mean, 6.02 times 10 to the 23rd is a lot. We're going to be learning about just how big is that number here in a little bit. So the mole is sometimes it can be written either way as M-O-L-E or M-O-L is kind of like the abbreviation. And all it is a unit of measure for a chemical substance. Okay? Again, we talked about a mole being Avogadro's number of particles. So those could be atoms, those could be molecules. And so what we're going to use in this unit is something called a conversion factor. So 1 mole is the same thing as Avogadro's number, which is the same thing as 6.02 times 10 to the 23rd. Now we're going to use kind of these conversions in order to do something that's called dimensional analysis, which we'll talk about here in a little bit. So we're going to use this relationship to be able to convert back and forth between different units of chemical substances, because the mole is a measurement of a chemical substance. So what are some other conversions that you might know? So here's one that you're unfamiliar with. 1 mole is Avogadro's number, or is equal to Avogadro's number, which is 6.02 times 10 to the 23rd. Some other conversions you might be familiar with are, well, 1 dozen is, well, 12, right? That's a conversion. A gross is 144. A baker's dozen is 13. Okay, these are all conversions that you know of, like how many inches are in a foot? Well, 1 foot is 12 inches. Okay, these are all conversions. We've used conversions for a long time. You've used them for a long time. We're just going to kind of do it in something called dimensional analysis. So just how big is a mole? We talked about it being 6.02 times 10 to the 23rd. What I want you to do right now is I want you to pause this video and I want you to go to this link. Now you can do that one of two ways. You can obviously type in this link, it's on your notes page, or you can actually search in YouTube how big is a mole. And you should be able to find that that video. It's a TED Ed talk that's going over a mole. If you're watching this video on YouTube already, what you could do is you could check down in the description, and I will also have this link down there in the description of this video to get to the video over how big a mole is. So those are some options for you to find that video. So I want you to stop that now and go watch that video. So now that you've watched that video over how big a mole is, it is kind of hard to imagine. So I've got some things on here that will show you just how big a mole is. So if you had a mole of softballs, okay, they would create another Earth. Okay, so if I had all 6.02 times 10 to the 23rd softballs put together in a big sphere, it would create another planet Earth. That's how big 6.02 times 10 to the 23rd is. That's how big 1 mole is. If I had a mole of Olympic-size shot put balls. Okay, those weigh I think about 20 pounds each. They would weigh the same mass as the Earth does. That's a lot. Okay, so that's just how big 6.02 times 10 to the 23rd is. All right? So that's a big number that we're going to be using to convert back and forth. Okay? So what we're going to look at for mole calculations is we're going to be using a method that's called the dimensional analysis method. Now, here's how the dimensional analysis method works. And how I'm going to be kind of going through this with you guys is I want you to write down the dimensional analysis. So you're going to have to be writing down some stuff on paper and keeping track of your work. And I'm going to be quizzing you over that throughout this unit. So the first thing you do in dimensional analysis is you're going to write down the unit that you're being asked for. The second thing you're going to do is write down the number in the unit that you've been given. Then you're going to apply what are called conversion factors in order to convert units. So one conversion factor that we've learned so far is we know that 1 mole is 6.02 times 10 to the 23rd particles. Okay, that's a factor conversion, okay, or a conversion factor. Okay, we'll be using that. So kind of looks something like this. You'll kind of write down your unit that you should get, write down the unit that you've been given, and then you'll figure out and use conversion factors to convert between those units. As you get more comfortable with this, hopefully it makes a little more sense. So we're going to use something familiar first. Before we dive into converting between moles and particles and all that, we're going to do something familiar. So here's your question. How many dozen donuts are in 63 jelly-filled donuts? Okay, so we want to know how many dozen donuts we have. So the first thing we do, again, step one, is we write down the unit that we want. Well, we know that we want dozens of donuts because it said how many dozen donuts. So that's what we're going to be asked for. That's what we're looking to find. So that's going to be the unit we're going to finish in. Step two is we know how many donuts we have. Okay, so this is the number and this is the unit that we're given. We're going to write that over here on this side. Then we have to think about what unit conversions do we need in order to go from donuts to dozens of donuts. Well, we know that 1 dozen is 12 donuts. That's our conversion factor. Now, we're going to write this one of two ways. We're going to write it as a fraction, where we're either going to put 1 dozen on top and 12 donuts on the bottom, or we're going to do it the other way. We're going to put 12 donuts on top and 1 dozen on the bottom. And I'll show you how we determine that. So we start with our unit over here. We know we need to end in dozen. We know we have 63 donuts. And we're going to use, this is again the dimensional analysis method. And what the benefit of this is it allows us to keep track of units. In science, units are very important. Okay? So we have 63 donuts. Now we're going to write this as a fraction. We're either going to put 1 dozen on top and 12 donuts on the bottom, or we're going to put 12 donuts on top and 1 dozen on the bottom. You might say, how do you know which way to do it? How do you know which fraction to use? It depends on this unit here. If I see donuts here, whatever unit I have in my given unit, I want on the bottom down here. Okay? So, since I have donuts here, that means I'm going to put 12 donuts on the bottom of this fraction. And I'm going to put 1 dozen on top. So it should look like this. So I've got 12 donuts on the bottom and 1 dozen on top. Now, just like in math class, when you have a variable on the top of a fraction and on the bottom of a fraction, what can you do with it? Well, you can cancel it out. Okay, so if I had something like 2x over x, I could just cancel out the x's. I'm going to do the exact same thing here. Because I have donuts here and donuts here, I'm going to cancel those out. Okay? Those units are going to be eliminated because they cancel out just like variables. Which leaves me with just this unit, which is dozen. And that's the unit that I wanted to end with in my problem. So that's how you know you'll be done with your conversions, is when the unit that is left from your dimensional analysis equals the unit that you wanted to end in. Okay? So now I would just do this math. If a number is on the bottom of a fraction, I divide by it. So what I would type into my calculator here is I would do 63, and then even though this is a multiplication sign, I'm multiplying by technically I do 63 times 1, and then I divide by 12. Now, multiplying by 1 does nothing, so I do 63 divided by 12, and that number should be 5.25 dozen. Okay, so that's how you use dimensional analysis. Now let's switch over and kind of do one that actually has to do with moles, which is what we've been talking about. So this would be on the back page of your notes. So now we're going to look at this problem. So it says, how many sodium atoms are in 0.12 moles of sodium? Well, what are we asked for? Well, we're asked for to find atoms of sodium. Okay? Step 2, we know what number and unit we have. Okay, we have 0.12 moles of sodium. And what's our conversion factor? Well, we just learned, remember, 1 mole of sodium is the same thing as 6.02 times 10 to the 23rd atoms of sodium. Now you might say, wait a minute, I thought you said particles. Particles and atoms and molecules can kind of be used interchangeably. So maybe this statement might help. An atom is a particle, but a particle isn't necessarily an atom. So it's kind of like particles are like an umbrella, and so a type of particle could be an atom or it could be a molecule. But a molecule and an atom are not the same thing. So a molecule is a particle, but a particle is not necessarily a molecule because a particle could also be an atom. So those can kind of be used interchangeably. What really matters here is that we could also interchange and put particles here. Okay, 1 mole and 6.02 times 10 to the 23rd particles could also be used. So we know that we have 0.12 moles of sodium, so I'm going to start with that unit. Then remember, I can write this as a conversion factor. I'm going to put either 6.02 times 10 to the 23rd atoms on the bottom, or I'm going to put it on the top and then put 1 mole in the other spot. Remember, how we decide what to put on the bottom is by looking at this unit. I know that I have 0.12 moles of sodium. Well, since this unit is in moles of sodium, the factor that I want, or the unit that I want on the bottom of this fraction, is the one that has moles of sodium in it, which is this one. So that means I'm going to put 1 mole of sodium on the bottom and 6.02 times 10 to the 23rd atoms of sodium on top. So now how I would do this math is I would do 0.12 times 6.02 times 10 to the 23rd, and then again dividing by 1 does nothing. Well, don't forget, I can cancel out my units. So I see moles of sodium here and here, so I can cancel them. You'll notice all that I will have left is atoms of sodium, and that's what I wanted to end in. Okay? So then I would just plug this into my calculator. Now, in your calculator, I would suggest using Google Calculator. So I'm going to show you how to put that into your calculator really quick. So again, the numbers that I had was 0.12 moles of sodium, and I was going to multiply by 6.02 times 10 to the 23rd. My suggestion is anytime you use a number in scientific notation, like 6.02 times 10 to the 23rd, to always put it in parentheses. So I'd put parenthesis, then I'd put 6.02 times 10, and then I'm going to hit x to the y down here, this button. And what that's going to do is that's going to create an exponent for my 10. And I'm going to put 23. Then I'm going to hit equals. So my answer that I should get should be around 7.22. Now how you interpret this number is this e means times 10 to the, and then this is the power. Okay, so it's going to be, I'll show you kind of how that looks in our PowerPoint. So I should get 7.22, and then it said E plus 23. What E means is this right here, times 10, and then the number that follows that E is the power. So I would write this as 7.22 times 10, and then to the 22nd atoms of sodium, and that would be how I would solve that. All right? So that's how you kind of do dimensional analysis with converting units. All right? We'll practice this some more, so you don't have to necessarily get this right away. in order to do your conversions, but I am going to be quizzing you over writing the dimensional analysis. I want to see your writing on paper, because as we get down the road in other topics in chemistry, using this method is really helpful in keeping track of your units. Okay? So another problem we're going to look at is how many moles of potassium are in 1.25 times 10 to the 23rd atoms of potassium. Well, again, what are we asked for, what are we given, and how do we get there? So the first thing is we want moles of potassium. How do I know that? Because it said how many moles of potassium. Step 2, we have 1.25 times 10 to the 23rd atoms of potassium right here. That was given to us. And how do we convert between moles and atoms? Well, we know that, again, 1 mole of potassium is equal to 6.02 times 10 to the 23rd atoms of potassium. So that's going to be my conversion factor. So I start with my units. 1.25 times 10 to the 23rd atoms of potassium. That's my given value. And then I ask myself, okay, I'm going to turn this into a fraction. And what am I going to put on the top and what's going to go on the bottom? Well, since this unit here is in atoms of potassium, I'm going to use my 6.02 times 10 to the 23rd atoms of potassium, and I'm going to put that on the bottom. Okay? And that means 1 mole will go on top. So what I would put in my calculator now is I would do 1.25 times 10 to the 23rd, divide, and remember, I want to put that in parentheses, divided by, in parentheses, 6.02 times 10 to the 23rd. Now my units are going to cancel here. My atoms of potassium, I have units of atoms of potassium here and here. Those are going to cancel out. The unit that I'm going to be left with is moles of potassium, which is what the problem asked me for. How many moles of potassium? So you can pause the video if you'd like and kind of do this calculation, type it in the Google calculator. I suggest giving that a try. And if you have any questions on how to enter in those values, make sure you let me know. And that would give us 0.208 moles of potassium. Okay? Now let's talk about how we calculate molar mass. So, what is molar mass? Well, the atomic mass of any substance expressed in grams is called the molar mass. Okay? So, the atomic mass of a substance is given on the periodic table. So, if you look on your periodic table right now, and let's say you find iron. Iron's symbol is Fe. If you look right underneath iron's symbol, you're going to see the 55.85, or a number very close to that. It might have more decimal places. That is its atomic mass, which means that the molar mass of iron is 55.85 grams per mole. If I had 1 mole of iron, 1 mole of pure iron, I would have 55.85 grams of it. Okay? Now, oxygen, remember we talked about this in our chemical reactions unit, oxygen occurs naturally as something called as a diatomic molecule, which means oxygen O2, if I look on the periodic table and I find its molar mass, it's going to say that it's 16. Well, O2 has 2 oxygens. So if I wanted to find the molar mass of O2, I would take 2 times 16, because every oxygen has a molar mass of 16 grams, but because I have 2 of them, I would do 16 times 2, which would give me a molar mass of 32 grams per mole. In other words, if I had 1 mole of O2 molecules, it would weigh 32 grams. Okay, so let's look at maybe one that's a little more complicated. So the molar mass of the substance is the sum of the molar masses of my element. So the last 2 examples were just elements. What if we have a compound? Okay, so let's look at something like MgNO3 which would be magnesium nitrate. So if I had to find the molar mass of this substance, I have to find out how many of each element I have. Well, I've got 1 magnesium. You might say I have 1 nitrogen. I actually don't. I have 2 nitrogens here. Because remember, this 2 on the outside means I multiply everything on the inside by 2. So I'd have 2 nitrogens and I'd have 3 oxygens. So you could calculate it that way. You could go, what's the mass of magnesium? What's the mass of 2 nitrogens? What's the mass of 6 oxygens? Add it all up. Here's another way to do it. Another way to do it is to take 24.31, that's the mass of magnesium. Then what you could do is, because this 2's on the outside, I could add up what all these are. In other words, I could add up 1 nitrogen and 3 oxygens, find what that mass is, and then multiply it by 2. So that's what I did here. 1 nitrogen is 14.01, and 3 oxygens would be 16 plus 16 plus 16. Well, that's my NO3. Adding that up would be NO3. But then I've got 2 of them, so I'm going to multiply that by 2. Either way you do it, you should get that the molar mass would be 24.31 plus 2 times 62.01, which would give me 148.33 AMUs, which you don't really need to know necessarily what AMU means, but what that does mean is that the molar mass of magnesium nitrate is 148.33 grams per mole. In other words, if I had 1 mole of magnesium nitrate, it would weigh 148.33 grams. Okay? So again, what you should be able to do from this video is you should be able to know the number of particles that are in 1 mole. You should be able to calculate the molar mass of a substance, and you should be able to now convert between particles and moles. Okay? Thanks for watching.